Hi, yeah, it's me again. Gonna talk a little bit about something new that we started this year with our friends at ACM Cyber. That's the Embedded Capture the Flag competition. And so really the kind of the goal of it is to do embedded software design to both meet functional and security requirements. And so this year's challenge involved a medical device. And so Andrew here is going to talk a little bit about the design work. Down is the next slide.
Okay, so this is the board we had this year. Basically every year for ECTF, Meter actually chooses like a different board, and this is this year's board. It was from one of their sponsors, which is probably why they chose it. And this is kind of a terrible board. I'll kind of get into this later. Last year the board they used was actually the same one we used in EC3 for the TI car. This year's board is completely insane. It's actually a pretty cool board. It has both an ARM CPU and a RISC-V CPU on it, as well as a quote-unquote CNN accelerator, which we did not use as this is not an ML lab. It has 512 kilobytes of code space, only 64 kilobytes of RAM, which basically means you can have absolutely no heap on this. This is like, there's only stack space. There's no place to put basically any data on there. It's bare metal code with very strict memory requirements. And so we were like, maybe this is a good use case for something called Rust. Now, I know most of you guys are EE majors, so you probably don't know too much CS, but there's a really cool new language on the block called Rust that does a lot of really cool things. So like we basically we looked at all the registers and where they're all in memory. We figured out how to get the SDK bound to Rust, and then we're off to the races, right? This is some beautiful attestation code. Except it turns out there's a lot of problems with this. One of the biggest problems we ran into was Meter, as part of the competition, we were required to use a build system called Nix. And Nix, unfortunately, is not the greatest piece of software. As it turns out, the latest version of Nix does not work on either Linux, Windows, or Mac. It somehow managed to be cross-platform and failing everywhere. This is actually amazing. They changed the build system for this year. Last year, again, this was a much more sane system with, I believe, Vagrant. So I don't know why they changed this. Also, Rust has a lot of good cryptography libraries, but there's a problem when you're trying to write secure software. You want those libraries to actually, be secure, and you want, somebody to have, gone through and audited them. And it turns out that a lot of the libraries in Rust, there's a lot of libraries for cryptography. A lot of them have not been audited. There's only, a couple libraries that we find that were audited, things like hashing, or I think SHA-512 was the SHA crates were audited, but things like key derivation, something like Argon 2 was not, and that was kind of important for our algorithm.
I'd also like to add, of the ones that were audited, a lot of them had to use the heap or use dynamic memory, so we couldn't use those either.
Yeah, again, we are restricted to literally 64 kilobytes of memory, which is a very tight constraint. And also finally, probably our biggest problem was it turns out Rust as a language is very hard to learn, especially if you only have a couple of weeks to do it. Rust is very nice as a language because it helps you identify a lot of bugs that languages like C and C++ won't let you identify. For example, in the SDK, there's these two methods which are absolutely baffling to me. So you have the method that reads from flash memory. It takes an address, the pointer to a buffer, and the length of the buffer. And then you have the write method, which takes an address, the length, and the buffer. Notice how those two are swapped. This is one of the many points in the code given to us that we were just what is absolutely this? What is embedded programming doing? So this was kind of a nice part about learning Rust is that you kind of Rust kind of basically tells you when stuff like this comes up. But unfortunately Rust with safety comes a pretty huge steep learning curve. A lot of times when we were doing this, people were asking what is a vec? Why doesn't it work? The vec requires memory, which we don't have. And what is a slice? Why does that work instead? Things like that. Now, despite all of those issues, we still actually managed to do a lot. We implemented most of our cryptographic primitives. So if I go back to the first slide, actually, there's this little diagram of all the things we implemented. Basically, on this board, there are three components to it. There's a center board, and then there's two sides to it, which we call the component, I guess. And then the center is the application processor or something. And so basically, the whole idea of the competition is that we have to design a protocol that in which the center board communicates the sideboards without leaking any information and without letting you figure out what the code on it actually does. And so we came up with this protocol. Huge shout out to Tom for helping us build this. He kind of he basically just wrote this entire protocol and then dipped. Amazing. But basically, this protocol, it lets the host figure out where the components are, and then it lets them secure them and make sure that the components are in fact actually real components and not hacker injected stuff. So pretty cool. And then what else did we do? Finally, we also did manage to do a lot. We actually managed to get a decent amount of Rust. A lot of the base code provided to us was written in C, so we rewrote a decent amount of Rust, and we found a decent number of really interesting bugs in it as well in the process of doing so. And in the end, we were kind of just actually bottlenecked by a lot of hardware testing. The debugger given to us something called Open On-Chip Debugger, and tended to actually work really well for code. But unfortunately, debugging your code is not as fun when the hardware itself has bugs. I read the spec for this thing, and this does not implement I2C correctly, somehow. And speaking of I2C,
so as part of ECTF, there's sort of two phases: attack phase and defense phase. So effectively, you have a part where you're writing all the software, and there's a second part where you're going to be attacking everyone else's software and hardware. So that was one of the things we were working on, is actually implementing an I2C attack where we would be able to read what other people were transmitting from one part of their board to another part of their board, and then intercept that data and change it to whatever we wanted. Unfortunately, we didn't make it to attack phase, so we were never able to test with other people's boards. But when we went to the ECTF award ceremony, we found out some pretty funny information. So ECTF provided us with a travel grant to go to Boston to go to their final award ceremony where it announced who won, at which point we discovered there were some significant issues with the I2C implementation. They provided us an example C code that actually had a critical error. You'll see we have a fun diagram provided to us from CMU in which about 85% of teams had their entire design fail because they copied this error into their final code. And then CMU was able to make an automatic exploit, so as soon as a team entered attack phase and their design was published, they would immediately attack it with this I2C attack, and within a few seconds they would have all the flags, which is the goal of the Capture the Flag competition. And yeah, it was pretty fun. We're able to see all of everyone's final results, and you can even vaguely see us in one of the official photos. They had a table in the middle. And we were also able to see people's other hardware attacks. So I2C was a software-based attack, different from what we were planning to do, which was a more hardware-based I2C attack. And we also saw people went to some crazy lengths, such as desoldering components on the board in order to break voltage rails, which is what is shown here with the oscilloscope. That's pretty cool.
Yeah, so we're gonna plan on doing this next year, and we want to actually be able to, first of all, enter attack phase and accomplish a lot more next year. So in preparation for that, we're planning on holding a lot more workshops in the fall, given the experience we've had with 1 year of ECTF. And this will help prepare people and actually help them understand what they need to do in this instead of throwing them into the weeds in week one of winter. So we want to hold these workshops in the fall. One topic that's really important is embedded programming. So being able to use Rust, knowing Rust syntax, and just different parts of the programming language Rust, especially for hardware constrained environments where you have no memory, or which libraries you can use if you have no memory, or what you can use in that case. We also want to teach about cryptography because this is really important in ECTF. A lot of the data that is transmitted or stored, you can probably just read it. So you want to have a way to encrypt that data and prevent it from just revealing all the information. So we want to teach stuff like key generation, hashing, stuff like that to store data securely. We also want to teach attacks on embedded systems like what Kai was talking about, different hardware software attacks that can be used to maybe read data that you're not supposed to read, stuff like that. We want to be well prepared for the competition next year, which again, it starts in the winter and runs into the early spring, so our workshops in the fall should be a good way to prepare for that.
Yeah, so if you're interested in cybersecurity or anything about embedded programming, make sure to show up to some of our workshops and see if you're interested in participating in ECTF next year.
If you're interested in taking an existing board and soldering the voltage LEDs together, maybe this might be interesting to you. Thank you.
I'm sorry, can you define what an embedded system is?
Basically, an embedded system is like, it's the concept of running code or running code plus like additional hardware components in like really constrained spaces. So for example, like this board right here, this is an embedded board. It's like, it has a microcontroller on it, but like this microcontroller isn't like, it's not like a traditional microcontroller or it like runs like Linux or Raspberry Pi OS. This basically only directly runs code with no other operating system support. And so because of that, like, it's very low level code. You have like, you basically only have code, you have like almost no memory to work with, and you just like, it's just a very constrained environment. But kind of as a result of that, you can build like very high performance applications using this. And these can be, because these are like, these microcontrollers have basically nothing in them. You can make them really tiny and put them into like actual medical devices. Think of like maybe putting them into your ear or maybe actually into your body. It's a really small device.
So it would be fair to say it's when you combine processing power, but you want to put it in a physical shell.
Yeah,
so
basically like
it's not
when
just
you want to take
computing.
like when you want to take the smartness of a computer but like package it into the size that would like fit somewhere really small.
For example, like in a UAV or something.
Yeah, something like that.
Okay, thank you.
How much time do you have for the attack phase?
We have like I think more than a month. Like
Yeah, so for attack phase, there's no set date where we have to enter it. There's a earliest possible date, and then the final possible date is when the competition ends. So anytime between those 6 weeks, I believe, you can enter attack phase. You put your design on the table for everyone else to attack, and then you get access to everyone else's design, so you can attack them. So up to 6 weeks.
yeah, this year like what happened is that like our team only met like once a week for like about an hour, and it turns out that was just not enough time to finish the design. So we'll definitely have to rethink about how often we meet next year. But yeah.
And is I2C a requirement for this project, or can you engineer your own
It was
protocol
not
that would
required. It
be more
was.
difficult?
I guess it wasn't really a requirement for the project, but like your solution had to work with the existing board, and I2C was basically the only thing you could do. Like you're not allowed to modify the board before attack phase, so you have to use basically what they give you. Like this board is given to us by Meter, so you have to basically use exactly what's on here. And I think I2C was the only protocol available.
Do you think it was on purpose that they gave you a bug?
I mean, intentionally, like they give us starter code for like this. That starter code is written in C, and that starter code intentionally is riddled with bugs. So one of the reasons why we chose Rust actually, that forces us to look at the starter code, and it forces us to evaluate. Wait, no, there's a severe bug in this. So for example, like the bug CMU found something that the low level, the starter code, the low level I2C code they give us, like they basically like they have a write to register function, which basically takes a length and then a certain amount of data. Except that length is never checked for like how long, if it's actually longer than the underlying data buffer. And you can, so basically you can tell it to write 99 bytes over I2C, and it just does that, which overwrites memory and causes like all the fun security issues.
Effectively, the
That was, like, the bug.
I2C bug allowed attacking teams to execute arbitrary code.
Yeah.
So it was a very severe bug.
Yeah, and we discovered this very early in our own development, and we did fix this early in our development as well. So had we actually finished our design in the major attack phase, CMU would not have been able to pwn us like that, basically.
There's a lesson there.
Yeah.
Yeah.
Any other questions?